Hi, welcome to the presentation about multiplayer games and parallel programming, which is actually only the first part of presentation. I decided to make also the second part, which is how to make extraordinary games in HTML5 using Node.js. So as I said, this presentation has two parts. In part one, I will present you briefly two games that I made, the only two games that I made so far. The first one is DuckHunt Missouri, and the second one is GoKart New Mexico. In those games, I will demonstrate mostly the network communication used in the games. They are both multiplayer games, which will enable us to make an analogy to parallel coding, which is message passing and message passing interface. It's OpenMP and OpenMPI. I will not speak much about parallel coding, but I will give you directions how to proceed if you want to pursue that topic. We also have introduction, which I suggest that you watch, but then after introduction, which is only one slide, you can skip to part two of the presentation. In part two, I will show you how I actually made the game, the GoKart New Mexico, and I will not speak too much details about this network solution that I needed for the game, which in game 2, obviously Socket.io was not good enough, so I had to leave it and use different type of protocol, which is the whole point of the presentation 1. So in second part, if you prefer maybe to see how the game is made and what the game is doing, what is the mechanics of the game, you can skip to part 2. There will be a button to skip after we finish introduction. And then you can learn all about that, how that second game was made with the web workers and physics engine, network phaser tree for 2D graphics, 3D graphics with 3JS, how you make a car model, the sounds and the particles, which is, I think, pretty general. No one taught me how to make games, so I came up with this scheme on my own. So I don't think that's the best way to do it, but that's certainly one way to do it. So you can think about it. I think it's interesting. And then you can come back to part 1 when it will have more context. But also, if you just watch part 1 first, it should be good enough. Okay, the introduction slide, before I give you the option to skip to second part, is what I use for making both of these games. So I'm using Node and JavaScript, JS. And let me start from the simple part. JavaScript is a language that is ran in a web browser. So each web browser has its own JavaScript engine that is running your JavaScript code. It's a runtime environment, so in Chrome, that JavaScript engine is called V8, and this one is considered to be the fastest one, I think, and I'm mostly using Chrome, but you also have SpiderMonkey in Firefox, Chakra in Internet Explorer or Edge, and I don't know what it's called in Safari. That's the JavaScript. So this is the modern way to make the web pages. And on the other hand, we have Node.js, which is actually a runtime environment to execute JavaScript code outside of the browser. Why would you need that? So you would need that to run the code, but to be able to do things that in browsers it's impossible to do because mostly of the security or whatnot. But for example, with Node running the JavaScript, you can access the file system on your computer. You can do some types of server communication and some other things that in principle you cannot do in the browser. So this is why we need Node.js. And very simplified, Node.js is basically one of the JavaScript engines V8 married with some C++ code, which enables you to do very nice things as a self-standing code on Windows, Mac, or Linux. And there is numerous packages that you can install in Node.js. They are called NPM packages, Node Package Manager. So you can install many codes, and many of these codes we will actually need to make the games. Okay, so this is part 1. If you want to skip to part 2, press the arrow here, and it will take you to part 2, and then after you see how the game is made, you can come back to the part 1. But if you want to continue with part 1, so let's go with that. My first game is DuckHunt Missouri, and in this video you can see how this game is actually played. So the novel idea in this game is that users can use their cell phones or the tablets with a camera, and that camera, using the computer vision, is used to calculate the aiming point, and then the users can shoot different objects on a screen. That game you can download from the webpage mobiletvgames.com, and there is a version for the kids and for the grown-ups. So here is the computer running the game and running the node, and this is like the browser tab open on a bigger screen, and then each of the players is running their own web browser. We'll see it in a second how it is structured. The second game is somewhat different, but again it follows the same idea of the interaction from the cell phone to the big screen, and it's basically driving a game where you use your cell phone as input command. So rotating the cell phone, it acts as a steering wheel. You have a gas and brake on a touch screen and some other commands. We'll see a bit longer video later when we explore how this game was made. So in a nutshell, both these games consist of the Node.js part that is running actually the server, serving all the web pages the browsers get. Then we have a main browser on a computer, which we call a server or a master, on which the master game is running. And then we have the browsers that are ran by clients on their cell phones, which are also connected to the server. You'll see in a second how. So, okay, let's see the structure of those games. So we have, typically on one computer, what we are running is that Node.js, so Node server.js is the server script, and we are running the Node server, and at the same time, we are running the browser, which runs the master game. What I'm drawing here is the CPUs and a number of threads. Here I represent like 4 cores, and each thread is running on one core. So we are just using one thread in each of those CPUs. Also, I notified here socket. So socket is kind of a communication socket that enables these objects to connect through network. So server has I/O, while the others have sockets, and each socket has a specific ID. And by ID, they can be identified on the network. The thing is, using the socket I/O as a node package, you can communicate only from the server to the socket client, so to speak. You cannot communicate directly from, for example, from this guy to this guy. So when you create the I/O on your server to which the clients will connect, so even this guy is called the master, he's basically just a client for the server. So you just create a server. I think I copied this from the code, but maybe this is not 100% correct, the syntax. Maybe I changed a little bit, but this is the idea. So you define your server, and you define your socket I/O package, and then your I/O, you define what happens on connection. So when one of those guys connects through the web address, then you define simply what will happen when this socket performs some operation, and basically those operations are just receiving messages. So socket on means what happens if this socket, for example, this guy connected, so each socket is defined with its specific ID, which is just a bunch of letters and numbers. So when it receives the message, you define the name of that message here. And here, for example, it's a bullet fired. So when someone emits the message with the name bullet fired, then we start a function. This is the message that was emitted, so the contents of the message, and then we do something, whatever we want the server to do. For example, then I do I/O emit bullets. You can check out socket.io cheat sheet. All the links and the things that I mentioned are most probably given below in the description of the video. For example, this one of the socket.io cheat sheets is given. So IO emit will send the message named bullets containing TMP variable, which can be different things. It will send basically this message to all the connected socket clients. And then you can define here other things like what happens if this socket sends update score message, and that message contains score, which can be a JSON file, so it can be very complex. It's not like score, it's just one number. It can be whatever you want, more or less. Then it will do something, so on and so forth. Okay, so let's see how it proceeds when player, using the cell phone, aiming on this screen, and then client or player presses the fire button, wants to shoot a duck. What happens is that socket on a client web browser code, that socket does emit bullet fired and sends the TMP variable, and that TMP variable is, as you see defined here, it contains coordinate X and Y where the user is aiming and he wants to fire a bullet at that coordinates. They are determined by the camera computer vision. You can see in the links the paper that explains how it is done, but that's not central to this discussion. So we have a message called bullet fired and some coordinates, and socket emit means that it goes to IO, and IO is running on node server. So this message goes here. And then, as we have seen in the previous slide, IO has defined already at the connection what will happen if this socket from this player sends bullet fired message. And it will happen very simply. The server will just emit the same variable. It will not change it. It will just forward this, but now with a different message name, so we can distinguish what is what. So he will just make a message named bullets, and actually that message will go to anyone who is connected to the server IO. So this client will also receive that message, but also the master will receive that message. So we are only interested what happens to this because client doesn't even have defined what happens in such message arrives, so it just ignores it. So this message goes to the master, and master socket, when what's created, it has defined in a similar way as server here, socket on, so on receiving the message that is called bullets with certain variable, it will take X and Y coordinates from that variable, and it will check if there is a duck on that position, so if indeed player hit a duck. In case the duck was exactly there, it will register a hit, so that's the game logic, and this socket will now emit new message, duck hit TMP. This TMP will now be something completely different. For example, it will be which duck was hit, how much it is worth in score, and so on and so forth. So, the same logic. Now this socket emits duck hit, and as I said, it can only communicate to IO, so it cannot send directly to the client, you hit a duck. No, it has to go to server. Server is like a middleman here. So the server IO receives that message, and upon that, for example, it will emit immediately the new duck, which is interesting for the master. So the master can create a new duck. The one that was killed is removed, but now the new duck is created with different velocity and value and whatnot. And it will emit update score, which should be heard by the client, and his socket on update score will execute some function of updating score, so the client can see that he hit the duck and he got some score. So this is a very simple network communication protocol that how you make your game engine work. Okay, so this is a multiplayer game, so the same logic applies if you have more players. For example, here we have 3. all of those three players are connecting to a server and they perform operations as I said before. If we just communicate X and Y when player presses fire, we get around 60 bits per second of network traffic per player. Or if you communicate the position of the aiming cursor constantly, so like I emit it whenever the camera makes a scan, you will get around 2 kilobytes per second per player. And there will be no significant lag. Socket.io that we use to do this uses TCP/IP network protocol. And this is crucial for discussing the second game. So this game is done in this way, and it works like that. So you start a Node.js server, which is I/O connection. The other entities have sockets, and they communicate through server. Okay, so following that, I decided to make my second game, GoKart New Mexico, with the same idea, basically. Only now it's a bit more complicated because I want to split screen. For example, here, if we have 4 players, I will split screen in 4, so each player can watch his own car. And the logic is the same. The clients will communicate to server, like their inputs, how much throttle, the steering wheel turning, whatnot. Server will communicate that to master, and master will calculate what happens with the cars in game, like how they move, if they collide, and this and that, and so on and so forth. Okay, that was my original idea, which is very simple, and you see that it suffers from the problem that we have to split the screen. So for 2 players, which is top and bottom screen, maybe it's playable, but still it's annoying to watch the other person's screen. 4 players is probably the maximum that makes sense. So I came up with a bit more advanced idea in which I introduced another master computer. So not only one master, but we have another master, or the second or third master or the fourth master. And then, for example, for 4 players, each of the masters would be running only 2 players, giving a bit larger surface of the screen to each player. So the logic is pretty much the same, but my idea was that you can run master 0 and master 1, and then player 1 can have his own screen, and player 2 can have his own screen, or we can have 4 players in this way. It's much more convenient than splitting the screen in 4 pieces. So this is the improved idea that we want to implement. Okay, so the same logic, we will have here the web browsers running. So I simply connect, instead of just one master, I connect another master, and we connect as much clients as we want. Let's say we want only 2, so each of the clients has its own screen. What happens in the game is that we have a car physics, which contains the car model. You can see it in part 2. What is the physics car model, which provides you, this is how you describe your car mathematically, which gives you the forces on the wheels. And once you have the forces, you apply the forces in the physics engine, which is Metro.js, which is it's relatively simple physics engine, because it's 2-dimensional. So I will be cheating here. I will use 2D world to make 3D game, which for the go-karts is probably okay, because you mostly don't notice the 3rd dimension with the go-karts. You will see how it works. But this is the idea. So you calculate the forces, send them to physics engine, and then physics engine moves the bodies of the cars, detects collisions, and moves them around. So the question is, where do we run this? So the physics engine, for sure, we will run on the web worker on master 0. What is a web worker? Web worker is when you explicitly activate another thread in JavaScript. So JavaScript by itself will not start new threads, I think. But with web worker, you can tell him, I want another thread, explicitly, and if your CPU has more cores, it will typically run on another core. While I'm doing this, I want to be sure that my physics engine runs uninterruptedly, not sharing one core with the main thread, because the main thread will also do the 3D graphics, the communication through the network and whatnot. So I want my physics engine to have the core for itself. And now we have to calculate forces first, because I said WebWorker will only do the physics engine once it has the forces. So to calculate the forces, what you need is car velocities and driver's input. You will see in a car model, if you want to understand it, go to the part 2 and find the car model. There it is explained how from driver's input, which is the throttle or brake and the steering angle, and car velocities, you calculate the forces on a car via car model, which is a mathematical model, which is just a formula. And those forces get fed into Matter.js, which is, as we said, will be running on a web worker on master 0. So how do you start a web worker? On a main thread, you define worker equals new worker, and then you define the script. This is the script actually of the code that your worker will be executing. So this script is actually listed here. And what you do with the worker, it's very similar as communicating on the network with socket.io. So you add event listener for messages. So this is message. This is not the name I invented. This is the keyword. You have to put message. And then the message is contained in E. And then E has, it's a variable that has data. And then in data, you can add whatever you want. But I put here CMD, which is like a command or a message name. So I put command is car's positions. It's very similar to socket.io messaging. So you make the name of your message. So my name message is car positions. So if message is received and this message name is car's position, do this and this and this. So it's pretty much very similar logic. And on the other hand, on web worker, you have also add event listener message function E. So if it receives the message, so this CMD is not given. You can call it whatever you want. It's a JSON object, so you can call it message name or whatever. So let's say that here on web worker, what I'm expecting, if I receive message that is called driver input, I will update my local variable car inputs with edata.driver inputs. And then you can communicate by post message, and then you put the JSON object, which is, this will be called data. So data.cmd, I give the message name car's position, and then I give positions. And this will go to main thread. On the other hand, from the main thread, if I call worker.postMessage driver input, it's the same logic. As I said, the code is not exactly correct, but this is how it looks like. Then it sends the message here, which will get recognized here, and then the web worker will do something with that input. This communication is very fast because we are basically doing it on the same CPU. It's actually just, they can share the memory, these two threads, these two cores. So I guess it's just a pointer forwarding or whatnot. But this communication is extremely fast. It has nothing to do with the network. It's internal in the CPU. Keep in mind, you can have more web workers, not only one. And it makes sense in parallelization logic. You can have as much web workers, it makes sense, as you have cores. So they don't have to share cores, because then you can like push your power to the maximum of using the CPUs. Okay, so what we have a master 0 that will be running the main thread and the physics engine in the web worker. We have master 1 that will be running only the main thread, so running the web browser. And we have two clients in this example, which will be running just the web browser in single thread. So what happens now? Equivalent to press fire button in DuckHunt, here we have player input. player's input is steering, throttle, brake, maybe player presses the horn, some other stuff, but we want to communicate that input mostly to master 0. We want it also to other master because we need to make sounds that player produces, but that's a bit further topic. So let's see how the physics works. So the player input goes through I/O, socket I/O to server, node server. Node server shoots it to main thread. Notice, I think you cannot communicate, at least not easily, directly from the web worker to the server. So I communicate to main thread, and then from main thread, I communicate to web worker, as we have just seen in the previous slide. This communication is extremely fast. This is on the network, and this is internal. So web worker got the player input. Web worker then does tick of a physics engine. The cars moves, and now it has to communicate those cars' positions to everybody else. So everybody else can draw the cars, the new positions, because the masters are drawing the 3D graphics. And the player can update the car velocity because on the player side, you have a speedometer on your screen, and maybe you hear the sounds of the other cars and so on. So web worker sends this to the main thread because it cannot send it directly to server. Then the main thread sends it to server, and then server tells everybody else what are the new car positions. So this is how it works. Player input is around 5 float numbers per player, while the car data is around 20 floats per player. So we have here obviously 2 cars because we have 2 players. So this is how much communication we are doing on the network. Okay, if you have followed who has car positions in player input, it turns out that we have all those info on a client, on a web worker, and on the main thread of the master 0. So on each of those spots, I can calculate forces. And those forces are needed at web worker. So web worker needs to apply that forces to cars in order that the cars move physically. That's what you feed the physics engine. To calculate forces, we need, as I said, player input plus car positions and velocity. I think we don't need actually the positions, we just need velocity. So we can calculate them on different spots. So let's think about it. What would be the best place to calculate forces? So we can calculate them on master 0 main thread, but there are only minus points to that. Master 0 already has lots of work, 3D graphics, communication, game logic, and whatnot, running the browser, running the Node.js, whatever. And if we actually want to do it there, we can simply fire another web worker on master 0. So let's say this is not the best option. We can calculate it on the cell phone on the clients. Notice that this is the most parallel place to do it, since player's cell phone is basically not doing anything. It's just sending a little bit of data now and then. And besides that, the CPU is doing nothing. And calculation of the forces is relatively simple, as you will see in the car model in part 2 if you go there. But this is the most parallel way in a sense. You can think that we can have like hundreds of players, hundreds of cars, or thousands of cars, and then it's almost no overhead to do. Even the formula is simple. If the web worker or master 0 should do the mathematical formula for 1,000 objects, it would become a bit slow. But now each cell phone for itself. So each cell phone calculates its own car and sends the forces. So the web worker doesn't have to do anything. It gets raw forces, just feeds them in the physics engine. And that's it. What is the potential minus? It's the lag. Because the cell phone, when it receives car positions, they have already traveled from web worker through the server, so through the middleman, and now forces have to travel back to web worker according to these car positions. So even if the network is very fast, you have to think that the physics engine is ticking very fast. It's ticking every 16 milliseconds. So definitely there is a potential problem that there will be lag. So these forces will not be up to date when they arrive to the web worker, which we will see that actually happens. We can calculate forces on the web worker. Web worker might have quite some work to do running physics engine, so collisions and so on, especially if you think in terms of running hundreds of cars, which is not probably very viable, but this is the way you think in parallel coding. You have to think in thousands of objects doing something. But the biggest plus is that it will certainly have small lag, or actually almost no lag at all. Once the player's input arrives, we calculate forces and apply them to the cars immediately. So this will be like in a sync, the most it can be from all the given cases. And also in principle, we could calculate the forces on the Node server. Because as I said, Node is also running JavaScript code, so you can just code your forces there and communicate them from there. I have something similar done in a DuckHunt game, where actually the server is preparing the targets for Master Zero. Master Zero is not doing targets himself, so it's a bit strange, but yeah, in principle, we can do it also here. Okay, let's do it the most parallel version. So calculate it on a phone. We said what are the plus and minuses, but what happens, you get very erratic behavior of the car. If you try to drive a car in a circle, it will not follow the circle. Your car will move really strangely, and it's kind of fun. The point is, even if your communication is relatively fast, it is not always of the same duration when the package arrives of the calculated forces. And to drive in a circle, this has to be very accurate. So the time application of the forces is different, and this causes erratic behavior. Notice that we are feeding the forces from the cell phone, not the input anymore. What happens on the web worker, so even if the player input does not arrive at identical time intervals, once it arrives, it will not change until the new input arrives. So let's say player turned the wheel 20 degrees to the left and put some throttle, and then web worker can actually simulate very nicely driving in a circle with that input, which does not change until the new input for player arrives, but it will look very natural. The car will go in a circle and it will behave very physically because the forces will be calculated at identical engine tick intervals, which I said is 16 milliseconds, which corresponds to 60 frames per second. And you will get very nice physical behavior. So because of that reason, I decided to go with this solution. So I will calculate the forces on the web worker because I do not expect thousands of cars, at least not for now. If I would have to deal with thousands of cars, maybe I would think of something different, but I decided to do it like this. As again, now for the third time I'm saying it, the formula of the car model is given in the second part. Okay, so how the game cycle works in a grand scheme of things. So let's start from the client. Player input, so the player is doing some steering, applying some throttle, or in DuckHunt pressing the fire button. So player input goes to server, and then server IO emits it to the master zero. Master zero forwards player input to web worker. Web worker from the car positions, which inherently web worker has, because he calculates them. He calculates forces and applies them on cars. Cars move, collide in a physics engine tick, and it produces new car positions, which are then communicated back to main thread of the master zero. Master zero then from the main thread communicates it to server, and then server IO communicates them to other clients or other masters. Why do we need to add on other clients? I already said that you needed to produce the sounds, for example, because this client needs to hear this guy's engine or the horn or whatever. So it needs to know the car position, also the car velocities, you will see in a second. Turns out this works pretty good. until we introduce master 1. So for master 1, it needs to receive also the car positions in order to draw the car for the client 2. So yeah, before that, let me say this is the situation where 2 clients are playing on the same screen on master 0. So that works great. But I want the other client to play on its own screen. I introduce master 1. And then master 1 starts showing obvious lag. So this guy cannot play because this guy has to receive positions from the main thread. And because there is a middleman, and due to the specific protocol that socket IO uses, which is TCP/IP, there is a lag here. So this doesn't work. I could have a game where all the players share the same screen. It would work fine, but that's not what I'm after. I want to run on like more than 2, 3, 4, 5 masters. So each one can have its own screen, each client. So it doesn't work. All of this fails. So it feels a little bit like in that joke when 2 persons are carrying a heavy couch on the 13th floor, and then one person says, I have a good news and a bad news. The good news, we are almost already at the 13th floor, but the bad news, we are in a completely wrong building. So yeah, it felt pretty much like that after I figured what I need to do. And it looked like it will be lots of work, but in the end, it turned out it was relatively simple to redo this game to work much better than with this socket IO. So how did I determine what is the problem here? It is how the scientific approach to the problems. What I did, I've drawn a graph here. So the green dots and the blue dots, I measure the timing from the bottom of the screen, and then I put the y-axis of the point proportional to the timing. And roughly this window is 30 milliseconds. So the green dots here, the green dot is drawn whenever I refresh the screen. So it actually shows me the refresh rate of the screen. So my FPS is, and it's 30 milliseconds. It's actually below, so it's below 30 FPS because I was running that on my old laptop from 2013. Now I can easily go to much higher FPS. But anyways, this is 30 milliseconds. And the blue dots shows you when I received the last message with the car positions. So obviously this is my master. Notice this is how I make connections. If here would be server, that's the server, but master is different master. This is master 1. And master 1 tells me that the time of receiving the car positions, first of all, it oscillates wildly with some of the points. Look at this guy. So this guy, before the previous message, there has elapsed more than 400, 500 milliseconds or even more, so half a second. The problem is the TCP/IP protocol ensures the time order. So if this guy got stuck, then no new message can come through until this is communicated. And that's the huge problem of this protocol. So the reason is that socket IO uses TCP/IP network protocol, which is optimized for the throughput and not for small latency. So I have very small data packages, as I said, just a few floats per car, but TCP/IP optimizing for the throughput, sometimes it sends more than one message in a single package, what is called, after 400 milliseconds or so, because it is optimizing for throughput. And then for 400 milliseconds, I have nothing happening on master 1, which looks horrible. So your car just gets frozen for half a second, and that's equivalent of having 2 frames per second or even less. So yeah, your graphics engine is running fine, but you simply don't get fed the new positions of the car, and it looks like they are stuck. And what we care about, we only care about the last message that passed through. I don't care if some message is still waiting and I missed some car input or some car positions in between, if I receive a new message in like 60 milliseconds, not every 20 or so, I don't care. I just want that message. And the solution to the problem is to use different network communication protocol, which is WebRTC. All of you have probably used it a lot, especially recently with the pandemic. So this is the Zoom session where the WebRTC, which is real-time communication, is used to communicate video and audio in real time. So you can have nice chat with quite a few people. But the thing is, WebRTC protocol, it has also data channel. So you don't have to communicate only video and audio. You can also communicate data. And this is exactly what we need for this game. So long story short, we will try to replace Socket.io with something else that uses WebRTC, which is actually UDP, I think, network protocol, which is a bit different than TCP/IP. And what we will use is a peer.js. It's a node, again, node module that we will use, and it uses peer-to-peer communication. So unlike Socket.io, where all the communication had to go through server, what I do now, this server still exists. You can use the cloud server to do this for you. And what the server does, it's a connection broker. So this server just informs the other clients what is their IP address, their IDs in peer. So through that IDs, they can communicate directly with each other. So now I can do peer-to-peer, and I can communicate from player 1 directly to master 0, and from master 0 to players, and from master 0 to master 1 and master 2, and so on and so forth. Again, how this is done, it's very similar to Socket.io. So you have peer now. Let's say we want to communicate between master 0 and client. You create a new peer, which is somewhat equivalent of the socket. I'll say later why this is important. And again, you define peer on connection. So when someone connects, this is con, I call it con, but this is equivalent of what was previously called socket. So let's say this guy connected here, and through its con, I defined what this connection will do when it receives data. Again, this is a keyword, but then in this data that is actually received as an array, I use the 0th index of array to give the message name. For example, if this is driver's input, we will do something. The same thing is on a client, so this is more symmetrical than Socket.io. I open the peer, and what happens on connection, when I receive data, if I receive cars have moved, we will do something, and so on and so forth. And then communication goes, connection send. You have to know to what this is connection to, and typically it's to master 0. So we send, again, we can send an array. I think it's a bit different syntax. You give, again, the message name. That's the most important. You give the message name, and then you give the variable. For example, I send the message driver input, but then in that message, I send the steering, the throttle, whatnot, as a JSON. And also I'm sending, this is my construction, so I'm always indexing a message. So as this client is sending its inputs, driver's inputs, which are read from the gyroscopes or accelerometers of the cell phone every 20 milliseconds, whenever I send a new message, I increase the index. So this guy knows which one of the received messages is the newest one. That's very important that here I put reliable false. So I told him I don't care if they don't come in timely order. Otherwise, you will run exactly in the same problem as Socket.io. It will be even much worse. But if you do this, then this is eliminated, reliable false. I think this is actually default, but still. And then let's say I got some message 100, there is a player's input, but it gets stuck somewhere in a network. And then I receive message 105 and I applied, but then message 100 arrives and tells me, oh no, the driver is steering to the right. and I just ignore it because here I keep count what was the last number of the message I received. So if I received 105, I will not accept anything under 105 after that. It's a very simple logic, but works very well. In the same way, you can communicate from master 0 to all the connected entities, but you have to name somehow logically your connections. So for example, connection to player 1 is player 1 connection. Send, and then you send again, you define a message name here, which is just the array 0, so you can put it wherever you want, but this is how I organize the logic at least. I put the message name, and again, I send car positions, of course, but again, I'm sending car message index. So I'm counting when this message was sent. So again, this guy, if it receives the older message later, it will just ignore it. So what we have, peer-to-peer, can you show that? Oh my God, sorry about this. I'm not sure if I shown that slide. What? Okay. Oh, I see now. So what we do, master 0, which is running the game and the web worker, so he knows all the positions of the cars. He communicates the car positions to everybody else directly. And the clients are feeding master 0 with the player's input, so it can steer the cars and whatnot. Notice that by this, master 0 has a large overhead in what it has to do, at least on the network. So one of the typical things that you do when you organize a parallel code, when you have a situation like this, that one node has to do, it's called nodes in parallel coding, it has to do lots of communication. You can think if you can do it differently because it sends the same information. So what you can do, for example, instead of doing this, you can send data only to masters and to the client that is actually connected to master 0. And then master 1 will forward this data to its respective clients, and these other masters will send data to its clients. So it includes 2 communications, but it might be much faster than if this guy, main thread, is losing much time in sending so many communications, which might be in the end slower. So you can imagine in this way that I have, again, hundreds of cars. And especially if you think about I could have like tens of hundreds of masters, then it would be even worth to consider sending the communication to masters through the binary tree. So master 0 sends to master 1 and 2, and then each of those masters sends to its 2 submasters, and so on and so forth. But you see that with peer-to-peer communication, you have much larger freedom of how to organize the topology of your game communication. So this is how I did it. And indeed, after doing that, the game works very nicely. So what you can see here, again, the same logic, I'm drawing here some timings. So the green line is the time elapsed from the last frame drawn. This is the 30 milliseconds line, the red line here, and the red line here. So now it is above 30 milliseconds. This is my new laptop, which can do much faster, but I limited the frame per second, so I wanted to draw actually every 34 milliseconds or something like that. But what is interesting is the player's input is the pink dots. So you can see how the pink dots are fed from the cell phone. It's pretty good. There is some outliers, but as I said, we don't care if we miss some of those guys as soon as the next guy arrives. And you can see it here, the communication of the car positions is the blue dots on the master 1. And you see, again, we have some outliers here, but we don't care about them because now they are not blocking the communications of the next message. So you have to be very unlucky that like few of your messages get stuck, so you have nothing communicated in like 100 milliseconds or so. But typically this will not happen, only some of those will get stuck, but the next one will go through. So you will update and you will disregard the old message when it arrives. It can even get lost, because notice if the message gets lost, it's not big of a deal. Like nothing will happen in a game significantly, it will not mess up the game. So this is what it is, and you can see very nicely that the blue line is very, very low. The pink line does not have that much dominant low because the master 1 is connected to wire on my other computer through the same router, while the cell phone, of course, goes through the Wi-Fi. That's the reason why this shows. But this driving through the cell phone is so smooth that you just must try it. You can almost not see the lag. It's awesome. You can download the game in the link and you can try it, even though it's not finished yet, but you can do it. I don't know if I should say this here, it will be too complicated. The nice part of all these things with Peer.js is to connect to the server, you will have to go to HTTPS connection, which typically means that I will have to do some SSH tunnel through some site on the internet, which can be anywhere in the world, so that my cell phone allows access to the accelerometers or the camera. For both of these things, you need HTTPS. So that you would think that will kill my connection because my communication will go through some web server, God knows where in the world, but that's only for loading your web page, so to say. Once you start doing Peer.js communication, it will actually figure out the shortest route from your computer to your cell phone. It will again use your local network without you having to do anything. It's just awesome. You will again get the same graph, even though you use some server somewhere in the world to establish that HTTPS thing. So yeah, that's how it works. And now, why is this so tricky with the racing games compared to the first-person shooter games, which also answers the question, why am I running only one Matter.js? Why don't I run a second physics engine on Master 1 and Master 2, like the third physics engine, so on and so forth? The thing is, racing games are incredibly fast compared to first-person shooters. So if you think about it, at the velocity of your car, 100 kilometers an hour, which is 60 miles per hour, it's 45 meters per second. Oh, I should also put imperial units here. Whatever, it's 45 meters, it's 50 yards, I think. I don't know. So in 50 meters, your car travels 2.5 meters, which is a pretty large distance on a screen if you look at your 3D like presentation of the game. 2.5 meters, it's how much? It's like 8-9 feet in 50 milliseconds. So it's basically almost in like 2 frames, your car travels large distance. And the most fun part of the racing games are, of course, collisions of 2 players or with an obstacle. And they have to be accurate, because otherwise the game will look lame. And in my implementation, actually, I detect the ground type also through the collision. Only that collision is just a sensor. So I just sense when my wheel hit the sand for the first time or the asphalt for the first time, and from that moment on, that wheel is on the sand or on the asphalt. So if each master would be running its own physics engine, I would need to sync the engines relatively often, and even small out of sync because of this high speed and large movements in small time fractions would lead to funny sudden repositioning of the cars. So you can do this sync, for example, if you do some kind of game like Age of Empires or something similar like Command and Conquer, where you can do syncing every 100, 200 milliseconds and nobody cares if something moved a little bit, because the movement is not large and you will not notice it. First-person shooter games, on the other hand, they're very similar to my duck hunting game. So the input is not that complicated as in driving. It's just aiming and shooting. And where you were aiming like 50 milliseconds ago has nothing to do with where you are aiming now. Unlike in driving a car, where your steering is like continuously fed into physics engine, resulting in your car's response. So you cannot say it is unconnected. That's why the car or driving games are so much more difficult to handle. And also in the first-person shooter games, player movements are relatively slow. Even if the player is running and he's far away from you, he will not move like significantly in 50 milliseconds especially. And additionally, you are not sure if you shot the player or not, and the game will look very naturally, even though it is struggling a little bit with the network communications and whatnot. In racing games, this is simply not possible. So that's what was causing the whole issue with this network communication, and why I had to revert to peer-to-peer. Okay, now finally we come to the analogy of multiplayer games and parallel coding. As you might have noticed, the whole point is in message passing. The only difference is that in games, basically players decide what they will do. They send input, they fire a bullet, they do that, whatever they want. And in parallel code, you will tell players what to do. Calculate me this, add me up this 100 numbers, and so on and so forth. In parallel coding, it is called leaders tell followers what to do. For example, calculate these forces or whatever. Previously, leaders were called masters and followers were called slaves, but we don't use that terminology any longer. So we have leaders and followers. And typically what you have C++ and Fortran to implement that. And how do you parallelize the code? So you want to use all the CPUs you can get, or CPU cores. And the thing is, on one CPU today, we have quite a lot of cores, like up to 30 or even 60. And they can communicate without using the network. This is what we did in JavaScript with WebWorker, and they can share memory, moreover, right? This is exactly what we did with WebWorker. In parallel coding, this is called OpenMP, or shared memory sometimes. While we can communicate through the network, we have used Socket or peer-to-peer JS. In parallel coding, this is called MPI, message passing interface. And in a big cluster productive environment for this, it's very beneficial if you have InfiniBand connection, which is a super low latency connection. So it is basically as these two CPUs are one CPU. That's how fast that connection is. So for some tasks, of course, even the regular network might be sufficient, but for some very connected tasks where you work on basically the same data, you will need InfiniBand. Pretty much this game would benefit a lot from InfiniBand because I need all the data shared all the time on all the masters. So yeah, this is the analogy. You can look, I'll try to put some connections to MPI and OpenMP, some relatively simple courses, but this is the analogy. This is the analogy that was not obvious to me right away, but now it's so clear that making games and making parallel code is basically the same problem. Only difference is what I say here. In games, you have the freedom what each follower will do. Okay, I decided to make a short philosophical overview, which might be a bit strange or not, whatever. I have technology aspect, which is very simple one. So this is the very first time that I'm using the web browser technology and JavaScript, and I can say that JavaScript now becomes, and web browsers in general, are much more mature than like even 2 or 3 years ago. All of this is relatively new, Peer.js and this and that, and even the support in all browsers is not that good, and web workers even. But they become much more mature, and they're such a powerful technology that together with cloud, I think that your computer will only need a browser. So whatever you need to do, you just need a browser, and that's it. But okay, that's just my thinking about that. Another aspect, which is much more philosophical, is about message passing. So I would say that message passing is like the most important activity that humankind ever developed. Because I'm saying, and I'm not an anthropologist or anything like that, I'm a physicist. So message passing actually enabled us to evolve as a species and as a society. And I think it's tightly connected together, that one followed the other. So we developed as a species and as a society in one bundle. And all of that was mostly driven with message passing. Because message passing enabled us. Obviously, the animals probably do some message passing, but they are definitely not efficient as we are with the language. So message passing, as I'm now passing messages to you, enabled us to do parallel jobs in much more efficient way and to do much more complicated jobs that a single human could ever do. So I'm using a very rudimentary example, like hunting the mammoth. Probably one human, if it's extremely smart and lucky to make a trap for a mammoth or whatnot, could hunt a mammoth. But that was like an orchestrated effort, which enabled humans to hunt mammoths and then have meat, whatnot. Probably it was much more complicated, but much more efficient to hunt a mammoth, and probably less dangerous than for one guy to do it. So, yeah. On the other hand, parallel coding, sometimes people get scared or freaked out. What is a parallel coding and how do you do it? How do you add it to the code? As you have seen in even making a game, so when you have the possibility of message passing and you want to use it to in your code to use more resources, it opens up many more ways how you can solve your problem. There are much more approaches to solving a problem, and it's not clear immediately or even at all which is the optimal one, as you have nicely seen with my problem with calculating forces. That's why I deliberately did that force calculation in different places. I still haven't explored a few of the options. So, as it was not obvious immediately to me, that's pretty much the same task, making a multiplayer game and making a parallel code. And as I said, multiplayer game is only different in a way that your players or your clients are completely free to do what they want in their part of the code. There is no prescribed code, you have to execute this or that, except if it's what you need to do in a game. So, yeah. How does programming GPU fit into this story? It's pretty much the same thing. You can think of GPU as your very special client that can do some tasks very efficiently. So you will communicate a message to your GPU client like, you do me this pass Fourier transform on this data that I'm sending you, and then I will have these other guys do something else with the data because they are only CPUs. So all in all, this is how all binds together. And that's why parallel coding is so much fun and why it is not so straightforward to learn. It requires much more thinking because your particular solution for the parallel coding can depend a lot on how many resources you have, what is the hardware you are working on, like if your network connection is very fast or relatively slow. Like in our case, we had a slower connection through the network, and we have incredibly fast connection in the web worker. So we could fire up more cores on a single CPU, but to communicate to other CPUs, we had to use networks. So then you have to be very aware of what is your hardware and what will be running your code and whatnot. So when GPUs come in place, then the picture becomes even richer, but that's the whole point of parallel coding. So this ends the part 1. And we are coming to part 2, where I will actually show you how the whole game of GoKart New Mexico was made, besides this network communication part. So I could use some self-contained engine like Unity or Unreal, but I wanted some very specific things, and I wanted to learn more of JavaScript and Node.js. So I like doing things from scratch, so I know how everything works and how I implemented it. The way I implemented it, I just made up all of this stuff, how I bound it together. So it may be completely wrong or completely crazy, but it actually works, and I think it works quite nice. So as I said, you can download the game and test it. Okay, so here we go to part 2. For those of you who joined now, it is the making of GoKart New Mexico game, except the details of the network communication, which I explained in the first part. So, start with a demo, which is here. So the player connects with a cell phone using this QR code. You select your avatar and choose the color. This is what I want. I want the blue color. You will see why. This is your driver's license, and you hit play on the master, and that's it. You start driving. So steering your cell phone, you can see it here. I don't turn the phone here in graphics, but actually in reality I'm turning the phone. Now I turn on the head-up display by this button, and I can adjust the light of the head-up display. You can change the steering sensitivity, so notice the wheels now turning much sharper than before. This is another switch which is actually showing the waypoint here. You cannot see it. I'm moving the joystick, which turns the head. Pressing this button changes the camera, and now with the joystick I can look around. And now I press this button to put the shapes, and the shapes are nicely blue in a color that we have selected. And now we press the gas. There is a different configuration for the left-handed people. So now you press the gas, the car accelerates. I'm turning the phone, but you see it only by the graphics turning, but I'm actually turning my phone. And you can see that it's super smooth. You cannot know it until you try it, but trust me, it's super smooth. There is the particles here, the dust, the sand particles, the dirt marks, and the skid marks. The skid marks you should see soon. So this is the dirt marks from the sand. And now when I brake or when I skid in the curve, there's the skid marks. And now I'm taking the second cell phone and driving another car on other computer. So these are two computers connected to the same game. Notice the sound. That change of the frequency of the horn was the Doppler effect. So it changed the frequency with the speed. Yeah, as you can hear. There is a backfire with more particles. There is obviously collision. And I think what's important to see, the skid marks, like pay attention on the skid marks, they will change now. I will explain them a bit later. So the skid marks change now. So this is going from the 3D skid marks to the skid marks texture, because I wanted the skid marks to remain indefinitely on the screen. So this is the demo. Very quick, I know, but you can try the game yourself. So what were the ingredients for making this game? I used quite a few JavaScript projects. So Node.js to run the game server, which is mostly doing just serving the files. Peer.js for network communication. This is what the whole first part of the presentation is about. So you should go to first part if you're interested in this, but it's not relevant that much for this one. I used Matter.js for 2D physics engine. So notice that I'm cheating. So I'm doing a 2D. This is actually a 2D game. Only that I show it in a 3D and it looks realistic, because with a go-kart, there is not that much need to go to third dimension, and my racing track is flat. Even for that, we don't have a need. I use Phaser 3, which is a very nice 2D graphics engine for the games. I use 3JS for the 3D graphics. 3JS is a really nice 3D graphics engine. I use GyroNorm for reading accelerometers, which requires HTTPS to give you the access to the accelerometers. It's similar to accessing your camera for the DuckHunt Missouri. I again need HTTPS protocol. That makes it a bit more difficult to make it technically, but it's not relevant for the game. Art tools, I will just mention them. I will not show you how I use them. You can see it on YouTube. So Blender 3D for 3D models, all of those are free. I used GIMP for 2D graphics. I used Audacity for sound. And at some point, I extracted some parts of the Google Maps 3D terrain, just like a screenshot. You can do 3D screenshot, so to speak. So you get the 3D parts of the Google, even with the buildings or whatnot. We don't have buildings here, but you can grab the buildings with the textures and everything. I'll show you where it is, the link. And all of that is in HTML5 and JavaScript. So keep in mind that we are actually making a web page. So we are doing nothing else than the web page. And that is the reason that we will be dealing with the canvases, with WebWorker, and with WebWorker there also come off-screen canvas, which I'll explain in a second. That's a very nice option. So, in the game, we have players. Let's say we have 3 players. And the players on their cell phones, they provide some steering and a throttle brake, pressing the horn. That information gets fed through network to the car model on your PC. So on your web browser, on your PC, running also the node into main thread and the web worker running the physics. Player input is fed into the car model, which you will see in a few slides what is a car model, which calculates the forces from the driver's inputs and car velocity. And then it is fed into the physics engine, which applies forces to the cars as rigid bodies, and the bodies move and they collide and whatnot, and that positions of the car bodies is sent to graphics engine, which then shows 2D and 3D graphics plus sounds. Also, physics engine sends some feedback to the players, which is mostly the car positions, but also those forces actually get fed back to the cars. So if the car is close to skidding, I actually made the phone vibrate. So it's like very rudimentary force feedback. It doesn't work on an iPhone, of course, but on Android it's very nice because when you come to 80% of the maximum friction that you can achieve, your phone will start to vibrate and then you know that you are about to skid. So you should go easy on the gas or straighten your steering wheel. Also, feedback provided is needed to produce the sounds because you have seen that I can hear the other player's engine. For this, I need this communication. More advanced things in the game, mostly why I wanted to control everything. That's why I didn't rely on any existing engine. I wanted tire skid marks, and I want those skid marks to be in different colors. This is my special go-kart, which has all 4 tires in different colors. So I know which one is skidding, but in a release game, the color of the tires will be the selected color of the player, which in this case was blue, as you have seen. So he had also blue sunglasses. I want the skid marks to appear instantly, of course, otherwise it would be really stupid. There is also dirt marks. If you, after running on the sand, go to the asphalt, there will be dirt marks. But I want them to remain infinitely on the track. So even if you drive 10,000 rounds on a track, the skid marks from your first round should still be there. You will see how I achieved that. In the sound, I wanted to introduce Doppler effect. So you know this sound when the ambulance is approaching you with a siren, it has a different frequency, and then when it goes away from you, it has a different lower frequency. When it comes to you, it has a higher frequency and then it has a lower. So I wanted to implement that. It's actually super simple. You just need the car velocities known. I wanted some particle effects for which I used SPE. You can see it also below in the description. So for dust and sand. I wanted sunglasses in color and the lens flare. This is not connected, but I wanted sunglasses in color. I find it rather cool. I wanted the force feedback on cell phone vibrations, which is not available. You cannot do that on iPhone. I wanted head-up display with variable lighting. I wanted minimap, and I wanted a dashboard. All of this is, I think, pretty reasonable for this type of game. So players input, I use gyronorm.js, which is one of the node packages, npm package. I think this is the name. For iPhone, you need specifically to make a click interaction with the user. So user has to click some button to get access to gyro norms. The reason for that is really funny. I will not go into that. I'm also reading not only the angle of your phone, so basically this is how your phone looks once you start the game, and if you turn the phone, I'm reading the position of the phone, so angle beta it's called, but I'm also reading the speed of your rotation. And to make it easier, because it's not easy to put your phone at 0 angle, so I have some dead angle. If you are just close to 0, it will take your steering as being straight. so it's much easier to make it straight driving. And I'm also reading your steering speed. If you turn your phone very quickly, I will actually add some, I will provide a larger angle than it's actually read. Because of the network lag, I will try to compensate for that, even though the network lag is very small. But keep in mind, there are many tricks you can do by reading the gyroscope or the accelerometers. What we have here, the main commands are these two sliders, but actually you can press your finger anywhere here or here for the gas pedal or the brake. They get reversed if you choose as a player that you are left-handed. Then, so it's pretty obvious. You have a brake and a gas and a brake. If you press them all together, you will get some backfire and so on and so forth. What we have besides that is you have these two sliders. So this is the HUD, head-up display light intensity. This is where you turn on the head-up display, and this is turning the waypoint navigation. This is the steering sensitivity, so you can change your steering sensitivity on the fly. Okay. And here we have a small joystick, which enables you to turn your head, driver's head, so you can look around in the game. That only makes sense if you have a cockpit view. Otherwise, you will just see your player turning head. This is the gear shift, drive and reverse. This is cycling the camera, so you have different views of your car. And this is the sunscreen, so you can put it down, or in this case it is up, and it will be in selected color. In this case, selected color is this green that you see all around. We have a speedometer, of course. You can choose miles per hour or kilometers per hour. Oh yeah, and we have a horn. You can blow a horn. So this is how the game looks like when you are playing it for one player or one player on one master. There is some debugging info here, these dots. You can see it in part 1 what it is. So this is the view from the back of the car. This is from the cockpit. So this is with head-up display turned on. So this red one shows you the steering position. So this is not at the center. We are steering a little bit to the right. This shows you how much throttle you pressed, and this will be red if you press the brake. This is your speed. This is the navigation to the first waypoint. So waypoint 1 is there. So from the car perspective, it shows you this guy. Here we have accelerometer, the compass, again the waypoint. There is odometer here, maximum achieved speed ever. The speedometer, again the gas. I might change this in the final version. And here you have the navigation map, minimap. This is you, and this is your next waypoint, and the other waypoints are red. So the yellow one is the one that you need to hit. This is something about the mayor of Zagreb, but I will not speak about that. This is the view from the car cockpit. So here you have very nice speedometer that turns with the steering wheel. This number, this is from the beginning of, this number is from the beginning of the race, and this is your lap time. So this is the lap time, and the yellow one will be your best lap. So you can compete with yourself with the best lap time. Yeah, this is actually the video on the web page, and I use this video element to play it here as a 3JS texture. So this is video, the other is mostly textures. Yeah, and this is probably the biggest American flag ever. And that's it. So it's very simple. I put the track in the Monument Valley because I like that part. Okay, so the game structure. The game is basically a web page, as I said already, and that is the reason why we will be dealing with canvases. Through the WebGL, we will be using WebGL because everything else will be too slow to show graphics. There is a video element on the web page, which I already showed you. I will not mention it again because it's very simple to use a video for a texture in 3JS. And of course, there will be lots of JavaScript. But how do we produce that image of the game? It's actually rather interesting. So if I show you the whole web page with all the canvases that are there, but that are actually hidden except the game canvas. So this is the game canvas in a debug mode. So imagine you see that this image is actually overlaid here. This is for the debugging purposes of the physics engine. But what I'm doing, I'm running 3JS renderer, so it's a 3D renderer, and it draws its image on a canvas. It's a full HD texture or a canvas, but then that canvas I use as a texture in Phaser, and I just use this image that was rendered on a canvas, which is hidden. I use it here as a texture on a rectangle in Phaser, which is a 2D engine. There is another canvas, 4K large, so 4096 times 4096, where I'm drawing the skid marks. And this is the skid marks texture. I will explain later why I need that, but that is also used in the game as a texture. Actually, it is used here. It is used in 3JS, and then 3JS is used here. This is the Matter.js screen, so it runs on a web worker, and web worker is actually drawing it on something that is called off-screen canvas. That was one of the first things why web worker was introduced, actually, because people wanted to have a web page and then the main thread showing you the text or whatever, and then they wanted to have some animation running smoothly no matter what happens in the main thread. So you could do some database or whatever query in your main thread, and then your web page can get really busy with the main thread, and then your animation, it would be run also by the main thread. It will be jittery, it will struggle, because it would have to wait for the cycles. But if it's running on the web worker is running in a different thread, so it's completely uninterrupted. It will be perfectly smooth if you want some animation. It was a bit tricky how to do it, because due to security, it was not easy from the second thread to access the main thread canvas. So for that reason, there is an option that the main thread releases control of the canvas to the web worker, and then web worker uses that as an off-screen canvas. As you can see it here, I'm drawing the Matter.js object. So this is actually our car in 2D, which then just gets transferred in 3D world, and you see it as your game. But this is basically my game. Copying of the off-screen canvas to the main thread is rather slow. Copying this canvas from the main thread to the main thread is very fast. I don't know if this is the best option to do it, but definitely it works, and you can achieve like 60, 80, whatever frames per second on semi-decent card that I have in my laptop. But copying from the off-screen canvas to main thread, it's a bit slowish. So I use it only for the debug purposes. And here you can see it. Then I make a 3JS image transparent, so I can see the other canvas below, and I can do comparison. If the 3D object is hitting something here graphically, it has to hit it also in a material world. So this is how you sync the 3D engine and the physics engine. What I've not explained is, this number shouldn't be here. That's from the previous game. How do I put a minimap here, and how do I put these guys here, and a head-up display which is missing here? So for that purpose, let me show you how the game looks like for 2 players. So for 2 players on a single computer, it looks like this. And let's say that this player turned on the head-up display, and this player chose the cockpit view, and the second player chose the back view and didn't turn on the head-up display, otherwise it would appear here. But both players have minimaps, and they have speedometers, and yeah, that's it. How do we produce this in a game? If I zoom out what I'm drawing in Phaser, so as I told you, these images here are just copied from the canvas in 3JS. So 3JS is rendering 3D graphics to canvas, and that canvas I copy here with scissors. But in Phaser, at this coordinate, so further away from 0, 0, I'm drawing the head-up display objects, I'm drawing the speedometer, and I'm drawing the minimaps for each player. So here I continue on the left if I need more for more players. And I define special phaser 3 additional cameras. So phaser 3 is not 3D, it's just a version of phaser that is actual. Phaser 4 is actually coming. So I define a camera that is watching this part, and then this part through the camera I just project here in 2D. The same is with the speedometer, and the same is with the minimap. So this is how I create this game, because 3JS is not very good for doing 2D graphics. So this is why I came up with this crazy scheme how to do this. Skid marks. If you remember in that video, we had these skid marks, and they suddenly change in appearance. So what I create when the game starts, I create like 1,000 circles in 3JS. So it's like a circle patch, and then I position them as the real skid of, or if there are skid marks, dirt marks, and I change their color and their position, and I just position them where they need to be. So they appear instantly, and they don't need to get created. They are created at the beginning. But I also draw the canvas on a skid mark canvas that I showed you before. So I'm using canvas drawing method. So I use the same color and the same transparency, but it's not possible to get it one-to-one matching. So that's why you see a little bit difference when they are replaced. And when I went through using the 1,000 canvas skid mark patch, I replace the whole skid mark texture. So all of that was drawn, so I just replace it so all the skid marks remain, and I start using the patches from the first one. So I just reposition the patches somewhere where you don't see them, and then I bring them to the screen as they are needed again for skidding. And of course I continue drawing the texture and get it replaced. Notice that this is the trade-off. So using more than 1,000 of these skid mark patches would be a relatively large task for 3JS. Thousands is not much. But if I wouldn't use them at all, and I would always replace the skid marks texture, that's again a very large burden to replace the texture every frame, and it makes no sense. So here you replace it only when I use 1,000 skid marks from 3JS, and this gives very nice performance and gives me what I wanted. So the skid mark is, or dirt mark is created instantly, and it remains there forever due to construction. You have seen that my tires get dirty if I go to the sand, and then when I run from this, here is some dirt marks. You have seen it in the video. Then when you come with your dirty tires to the asphalt, they get clean after some time. So getting dirty and getting clean is according to distance traveled on a sand or on the asphalt. So I used actually the odometer of the car to calculate this. And as I said, if the car wheels is close to skidding, the cell phone will vibrate, and that's a very nice feedback that tells you that you are very close to the limits of the car in the curve or so. The car model. So car model, what is meant by it is a physical model, as a physical model is actually a mathematical model, which is simple description of a complex reality, which can be physical, social, economical, medical, you name it. So we all know that a car is extremely complicated device, but in this model, you can see the link below where I found this model. It's super simple. It literally requires you to calculate one angle. That angle is called the slipping angle. And what is the slipping angle? So you can see the car here. This is the orientation of the car, obviously. This is the front of the car. But it can happen due to, obviously, skidding, sliding, whatever, that the velocity of your car is not pointing in the direction of the car orientation. So you see that the car is going partially sideways. This is the VY, what I call here. And this angle of your car velocity deviating from the car front orientation is what is called slipping angle. Notice that velocity, so basically you want to see the wheel's velocity compared to this orientation, and you have to keep in mind that wheel's velocity is not only this, because this is a rigid body, it has a velocity, but it has also the angular velocity, omega, shown here. Let's say the car rotates on the right as well. So this wheel will have, I'm interested what is the velocity perpendicular to the car. So it is Vy in this direction. So it is the same as a car center of mass. But due to rotation, notice that this wheel will rotate in this direction. So from the right to the left, which will give him some component of the y to the left. So the velocity y of this wheel will be Vy minus omega times the distance from the center of mass to this wheel, L rear. The same will be for the front wheel, only it will be Vy plus omega times L front, because here the Vy is in this direction due to this rotation, and it will be plus. Additional complication is that you have the steering angle of the wheels, and that makes the slipping angle different for the rear wheels and the front wheels. And here I'm showing you the expression for the slipping angle of the front wheels. So it's basically arctangents of the Vy velocity of the wheel and the Vx velocity of the wheel. So you see that it includes the steering angle alpha. It includes the car velocity, Vy and Vx. That's why I told you. So steering angle alpha requires you that you know the driver's input. If you remember from my presentation, I mentioned that we will need to calculate forces. We will need steering input, which is alpha, and we will need car velocity, which is Vx and Vy, and also the angular velocity of the car is also one of the car's velocities. This is how you describe the rigid body movement. You have linear and angular velocity. And now, and from this angle, you are able to calculate forces on your wheels. So the lateral and longitudinal forces, and this is the forces that we feed to the physical engine. And then due to those forces, this rigid body will move, rotate, and whatnot. But let me show you as a physicist, how can you think? So for the rear wheels, this expression is much simpler. So it's only Vy minus omega L. This should be L rear, but I put that the center of mass is somewhere in the middle. Doesn't matter. So you can adjust this, divided by Vx. So this is exactly the ratio of those slipping speed and longitudinal speed. So this is the slipping angle. For the front wheels, obviously it's much more complicated, but what you usually do as a physicist when you have something very complicated, you notice the limit case. If the angle alpha is 0, so the steering is 0, I should get exactly the same result as for the rear wheels, only that here should be different sign, and as I explained, this rotation gives plus Vy here and minus Vy for the rear wheels. And indeed, if you put alpha equals 0, you will get Vy plus omega L over Vx, while here is Vy minus omega L over Vx. So yeah, this is consistent for sure, and I'm pretty sure the model is correct because the car behaves very physically, very believable. And this is your model. So this formula, this one formula, is your car model. This defines the behavior. Of course, there are some physical properties like this position on the center of mass, momentum of inertia of your car, the mass of your car, that will determine the physics of your car, but all of that is in a physics engine. That defines the rigid body. You don't care about that. This is what defines your physics of your car. Of course, we will feed the input, like what is the braking force or the engine force, depending on the throttle, but that's pretty much trivial. So you just apply forces. I consider that only the rear wheels can apply driving force. I actually made a model with a four-wheel drive, which is much more fun to drive, but never mind. And of course, we defined the friction factor for each wheel. So this is mu RR, rear right wheel. And in my case, it's very simple. I just have a different friction for the sand and a different friction for the maximum friction for the asphalt. And this causes different behavior on asphalt and sand. And since it's wheel independent, you can have a different behavior on the different surfaces. Okay, the racing track, how I did it. So the racing track is very real. It is in Pula, in Croatia. It's called Green Garden. You can see it here on a Google Maps, and you can see the guy driving on a YouTube. This is the track. It's very funny. So the guy has 28 horsepower go-kart, which is relatively powerful for the tourist go-kart. And his best time is 48:47 seconds, and the best that I could do was 48:38.3 after quite some training. And my go-kart, I made it so that it goes from 0 to 100 kilometers an hour, or from 0 to 60 in like five-ish seconds. Okay, so what I did, I basically went to Google Maps, I grabbed this, and then I draw the track in SVG using Inkscape. I maybe didn't mention Inkscape. And then using the SVG graphics, I feed it to the physical engine, Metro.js, and it calculates the polygons. And maybe I mentioned, so these polygons define objects, and the yellow one is the asphalt, and the black one or gray one is the sand. And then I'm detecting collisions. This is my car object with 4 wheels. I'm detecting collision of my wheel with the asphalt object or the sand object, but collision detection is only done as a sensors. So there is no collision in the sense that car bounces back from the object, but just detects it collided with the sand. And from the moment it collides with the sand, I consider this wheel to be on a sand. And the same way when it hits the asphalt. So it can happen sometimes that it doesn't register immediately that it hit the asphalt because maybe it's too fast, so it just misses the tick. This is, for example, real objects. This is the legs of some object that is here behind. So if you hit this, the car will bounce back. And yeah, all of that. In the same way, I use the SVG graphics to create the 3D, the track and the sand. But how I cover the track and the sand with a texture, it's not one texture. It is one object. So the track is one object, and the sand is another object. I forgot what's the name of that. It's some kind of mesh. But then I'm taking the asphalt texture and the sand texture, and I applied what is called decals. So I go around and I try to stitch the decal with random orientation and also varying the color. So what I get is nicely covered sand and asphalt, and you cannot see the repetition of the texture. So there is no array that you would see that it's repeating. I use around 200 points to cover the asphalt part and around 300 points to cover the sand. So this is how I did the 3D graphics. Speaking of which, the others are 3D objects. Some of the mountains are from the Google. We'll come to that. And there is a skybox. Yeah, we'll come to that. The sounds. So I recorded the sounds. You can see the engine sound is my Toyota Highlander V6 3.3 liter gasoline ethanol engine, 250 almost horsepower. So this is exact recording that I'm using in the game. So when I want to change due to throttle or the velocity of the car, I change the volume of this sound clip and I change the rate. So it ticks faster or slower, showing you the different revolutions of the engine and the volume. The horn is also my car horn. I did do some tire burning on the Highlander, but that was a bit difficult to record, so I just took something from the internet. And now we are coming to the fun part. So if you are player 1 and there is player 2 and 3 driving at certain velocities, and let's say they blow a horn, you will hear the horn of player 2 depending on the distance, but also depending on the relative speed. So you have to project this speed V1 to see how much you are approaching player 2, and V2 projected here to see how player is approaching you. Obviously, it will give higher frequency due to the Doppler effect, while this guy is driving away from you. If he blows a horn, his frequency will be lower. It's pretty fun. It's pretty fun, and Doppler effect, you can see it on Wikipedia what it is, but you've heard it in my video when the guy was blowing a horn and driving towards me and then passing me, you could see how the frequency changed. Okay, the Google Maps I almost explained. You have the link below, so it's possible to go to Google Maps in 3D and take kind of a screenshot by getting objects from your graphic card buffer together with the 3D structure and textures. I will actually show it in the next slide how I captured that. And 3D models, I bought some. Actually, there is in a game, there is 10 of those roasting pigs that they are actually revolving with some particles here of the sparks. I paid this one $19, I think. The GoKart I find somewhere for free, and then I modified it. 3D graphics, so the screen capture from Google Maps, here I already imported it in Blender. So this is the Colosseum in the same town where the track is, it's the Pula. So it's grabbed from Google together with textures, and actually at one point I put my game in the Colosseum, so we can race in the Colosseum. Like this literally takes the YouTube video that explains you how to do this, literally takes like 3 minutes or so. So you can choose whichever part of the world you like together with the buildings. You can grab everything in Google. Of course, if Google has the buildings, for Pula it has. So this is the game in Colosseum. Particle system, I use the SPE. I forgot what is the name. You can see it in the description below, the link to this. It's again JavaScript based on 3GS, but this particle engine is running on a GPU. So you can have lots of particles and it looks very nice. This is the effect I wanted. I wanted to spray the sand particles from the dirty tires, or when the tires are on the sand. So yeah, this is I forgot what is SP. This is the particle engine that I used. And this is how I make the testing. So I make very, very small chunks of independent code where I test, because all of this was completely new for me. So I had to learn everything from scratch, and then I make a small chunks of code that I test, and one of those is animation like this. So I used this car to learn how to turn wheels, to change the tire color, turning the front wheels and whatnot. I even wanted to implement mirror with a rear view camera, but that's a bit too demanding for the GPU, at least mine. Okay, sunglasses in various colors. You can see here the lens flare effect. That's the first thing. So that's a very simple effect that you have in a 3JS. But then I implemented the sunglasses. So let me explain in this image. We have a 3D objects, and we actually don't see any of the mountains. There is also the part of the Google Maps that is giving you the 3D mountains. But these mountains that you see here, it is actually the image that is wrapped around the sphere. It's called the sky sphere. So this is just the image as a texture. And then when I want to lower my blue glasses, what I do, there is a light source somewhere here. So I change the intensity of the light source, and I change the color of the light source. Of course, to this blue that is selected. And this works very nicely, but then this sky sphere, this image would not change. So I apply also this blue color to that sky sphere image. So you can do it independently for every render. You can change that. So if two players are rendered, like two screens, one screen when I call a render command, I apply one light, and when the other is applied, I apply different light if other player has different color of the sunglasses or doesn't have sunglasses at all. But this is a very nice effect, and I like it a lot. You can choose orange glasses, pink glasses, black glasses, whatever you want, and then you see that it reduces a lot the sun glare. I don't remember seeing this in many games, or at all. Okay, so how the game is organized, because besides the game itself, there is a menu scene where you choose your driver and whatnot, the end scene where you see the results of the race. So it's organized through phaser scenes. So when the game loads, so when your web page loads, basically your master has a load where it loads the sounds, the images, the textures, whatnot. Then I generate the three scenes, so the 3D objects and that, and then it reaches the menu scene, from which you can go to options scene and back to adjust the sound level and some other options. The client loads only images and sounds and goes directly to menu because the client does not run anything in 3D. And then the client has the avatar selection scene and option scene. And once they're in the menu, we can start the game by pressing the play button on the master. Then they both go to play scene, where they run both play scenes, which is communicating through network and doing the game mechanics, while the master is also running the web worker on another thread for the physics engine. And once the game finishes, they go to end scene, where it shows the result, the best lap, the highest speed, and the winner of the race. And then when you want to play again, it goes back to menu scene. So this is how it organizes in Phaser. The play scene itself, it takes place on a cell phone, which looks like this. It takes place on a computer, which has a master, main thread, which does the 3D graphics, and web worker in another thread runs the physics engine. So player's input gets fed to main master, to main thread, so steering, throttle, and brake. I just read the gyroscopes or accelerometers every 20 milliseconds. This is sent to master. Master then feeds that to the web worker, the player input, and based on that, web worker calculates the forces on each car, moves the cars, checks collisions, and sends that car's data to the master, which master uses to show us the new car positions, the sounds that we can hear, and whatnot. And also master sends it to the client, so the client can hear the sounds on the cell phone. It updates the speedometer, obviously, and if the phone needs to vibrate, if the physics engine says you are close to skidding, then it will vibrate. So in hindsight, making of this game took me around, the GoKart New Mexico game, took me around 600 hours. DuckHunt Missouri, actually the first game, took me even more, but that game was lots of testing because aiming using the camera was not that simple to develop. It was like developing the technology and implementing it in the game, so it was kind of a fun. And me also learning JavaScript at the time. I had no idea of JavaScript and how to use it, so it was all from scratch. So it took me even more, but I learned a lot. I spent lots of time on art, much more on 3D than 2D. In 2D, for the one game, I even followed the YouTube videos for like 4-year-olds how to draw, and then I draw some avatars for kids because there is a version of the kids game for DuckHunt Missouri. I didn't want the kids to shoot something live, so they're just shooting some rubber ducks and whatnot. Also, there is a very nice, it's a paintball guns for kids, so when they shoot, the paint gun splatters, and I wanted those splatters to remain infinitely on the board. This was my idea, the same solution that I applied here for the skid marks. Lots of testing, and I suggest testing in small chunks because I was introducing new elements like particles and this and that, and I had to learn all of that, how they work, and to test parameters, because at some point the game was already substantially large. It was not quick to test it. There were lots of problems caused by Socket.io moving to Peer.js, but that transition, however it looked like it will be a daunting task, it was actually very quick because I had only to replace like two functions because there's only 2 points of communication. So the player sending the input and the Meter.js sending the car positions through the master to everybody else. So there is only 2 communication points. But it was a bit cumbersome. So this shows you that you need very deep understanding of the technology you are using. It's obvious that you use WebRTC for video and audio communication, but it was not that obvious that it's necessary to use it for data channel in a racing game. Well, I never thought that making the simple web page will be so much fun. I'm somewhat embarrassed that I didn't realize it ahead that making a multiplayer game and parallel programming is actually the same task. It's basically the same structure, the same task, only that it has a different dynamics. In that sense, the game is more demanding, because if you do something wrong, like here with Socket.io, only your performance of your parallel code will suffer. It will run not as fast as it can, but your game will just not work. Nobody will want to play the game with 2 frames per second caused by the lag of communication on the network. So this is what is one of the main differences. Like, you cannot afford to do something wrong in a game. You have to do everything optimally, and that's the beautiful part on finding the very creative solution. So it's more kind of an art than a coding itself. Now in hindsight, finally, I think I could do a similar games within a week or 2 weeks tops. Especially if I get to hire like professional artists, so I don't have to watch a YouTube video and try to draw like a 4-year-old. Especially 3D, I got somewhat skilled in Blender, but still it still takes you lots of time. And as I got this as a fortune cookie in Linux, learning curve is steep, but you have to climb it only once. And my question is, developing this, that's why I called my website mobile TV games, or cell TV games. Why don't we see more of this cell phone TV games around? Because this interaction of the cell phone and the game is so much fun, because your cell phone is such a wonderful device. It has so many things inside, like from the camera to the accelerometers to the vibration to the touch screen. You can make incredible controller with a cell phone, as I demonstrated in these 2 games. At least I hope so. GitHub repository for both games is private. I distribute the games as self-contained executables using Nexa. Why is this private? Because it looks like hell. If you open the code, it's lots of experimenting, testing, fiddling, ad hoc planning, comments in English and Croatian. Like, yeah, it's kind of crazy how it looks like. Even though I think it's relatively nice code. Why I did it like that? Because I never thought I will go all the way to making a game. And also from the beginning, I knew that I would be doing this completely on my own. So I didn't pay too much attention on making like super nice structure, documentation, and so on and so forth. But I know how it is done, and usually don't do it all that. If you would like to see the code, I can definitely provide you the code. That code is actually, to make these 2 games, those codes are actually not much of a code. There is not many lines, as you might expect from such a complicated looking games. It's a relatively small amount of code. Okay, so before playing this, yeah, there will be references. This I will put in the description of the video. But here I will run what it took for me to create this game. I was basically making some scribbles on a paper, trying to figure out the structure, which shows you how artistic or creative is the process of multiplayer game creating. And I was doing some waypoints or milestones that I try to reach. So this is the 600 hours in the papers that I have lying around. Making the DuckHunt Missouri was much more difficult. It included writing the scientific paper, which you can find online. But yeah, with this, I'm finishing this presentation, and you can watch this video in silence, and after that there is nothing. So thank you for staying with me, and I hope you learned something. If you have any questions, feel free to shoot me an email, and I'll be more than happy to answer it.